So I may have a pleasure now to introduce again Rama for his last lecture, if I'm right,
Yeah.
on this series on Chern-Simons and knots.
Yeah. Okay, so in the morning I try to take a braid word which is b1 to the power of or b2 to the power of m, right? And then I did a closure. And this evaluation, everything is in S3. And this evaluation, the invariant, the normalized invariant, ambient isotopy invariant, for any, if M is even, you will get a link. If M is odd, you will get not, right? But you can put both the representation to be some arbitrary representation. It could be, if you put fundamental, then you will get the normalized version of Jones. You can put this one, you can put other representations. Any arbitrary symmetric. If you are doing SU2, if you are doing SUN, over on top of these, you can also have all possible representations. There is some kind of a cutoff which we have to remember, because these have to be representations allowed by the SU2K affinely algebra. Okay. So that cutoff will be that the number of boxes can be at most k. Okay. So you cannot, the first row should be at most k and the rest of the other rows in SUN should not exceed k. That's an important requirement if you are in the affine algebras. Okay. That you have to keep track. But otherwise, usually we assume k to be very large, these representations to be very small. So whenever we do the tensor product, which we were doing, this is fine as long as k is very large. If your k is 10 or something, this is fine. But if k is 1, you have to worry about. There is a cutoff which you have to put in. Those are the fusion rules of SU2K, affinely algebra. But this invariant, as I argued today morning, can be written as psi 0 with b2 to the power of m, psi 0, and then this evaluation can be written as summation over s, dimension q of rs, and then lambda rs, which is obtained from taking the crossing between two representations. And we are going to do parallelly oriented strands, right? All the strands on which we are going to do are parallelly oriented. So I am going to put the parallelly oriented as with the plus sign. And then this has to be right-handed braiding, and we have moved it. Okay? So this directly gives me, so the direct evaluation. No need to go through skin relation. And as a check, you can check with skin relation for fundamental whether these are matching. And this is the answer which will be true for any arbitrary closure of a two-strand. Okay. So the next thing is you should start looking at closure of a three-strand braid, right? You can have 3 such strands. We can do B1, B2, inverse, and then B1, B2 inverse. Okay. So you can take this as a braid word, B to be B1. So take everything to be parallelly oriented. B1, B2 inverse, B1, B2 inverse. Right? This is 1 and 2 is B1 and then B2 inverse, then 1, B1, B2 inverse. and then we close it. By closing I mean closure of a braid with identifying these points. So I can identify this way, identify this way, identify this way. So this ordering you can draw whichever way you would like to. Now we need to do the calculation for the invariant of this object, right? There it was much more simpler. We had a 4 punctured boundary. Now if I take any slicing anywhere, okay, so everything is in S3, so I am not drawing the S3 inside with this knot is there, so you assume. So this is an S2 slicing. The punctures are 1, 2, 3, 4, 5, 6. Okay. Incidentally, this closure knot is nothing but the figure 8 knot, and we would like to evaluate this. Okay. So we can do the evaluation in the long winding process. Only thing is, for a 6 punctured boundary, you need to start writing the states. Okay, so psi 0, let me call it a psi tilde 0. This should be a boundary with 1, 2, 3, 4, 5, 6. Correct? And formally I can start drawing it depending upon what I would like to do. Suppose I want to do the B1 operation first. The basis where I can do the B1 operation should involve 1 and 2. Okay. The remaining ones, 2, 3 and 4, I could put it this way. This is one possibility of basis. Where, so these are what will be the dimensionality of this now? Someone can see for fundamental, you will have an S. Okay. And then this one with this will give you a T, right? And these two should combine to give you a value S1. S1 should be such that this with the fundamental, right? This one also is S1. S1 with T should add up to give you a single. So work it out and see what is the dimensionality of this. Okay, so it's not that straightforward. Last time in the 4-point conformal block, you know that S will be, the values of S decides the dimension of this. But here the value of S, T, S1 together, what are the allowed values, you have to list it out and see what is the dimensionality of this vector space. Okay, I'll leave it to you to check this out. And once you have this, you can start writing the states in a suitable fashion. And then you do the braiding operation. Only thing you have to notice, it's okay to use this basis to do the B1 operation. But it is not going to be the same basis if I have to do B2. Why? Because B1 and B2 is not equal to B2 and B1. Whether you do inverse or not, I don't care. But this is not true. Because once you exchange 1 and 2, it's going to affect the second strand, which becomes the first strand, and then the thing happens, right? You can see this explicitly. B1 and then B2 inverse is definitely not equal to B2 inverse. Sorry. Okay. So you can number them and see 1, 2, 3. This becomes 2, and this becomes 1, and this becomes 3, right? The strands. You see here 1, 2, 3. So this becomes 3. This becomes 1. So it's definitely not going to be this. But if you do B1, B3, right? Because you can do 1, you can do 3, same as you can do B3 first and then you do a B1, right? So here it's 1 2 2 1 3 4 4 3 1 2 2 1 3 4 4 3. Okay, so as long as they are not consecutive, you can use the same basis. This basis I can use if I want to do B1 on this. So I will have the S, T, S1, let's say, right? What will this be? Okay. Fine. But if I do B3, fine. Because B3 will see the twisting between these two, and that twisting information is in this T. Okay. Fine. So if I want to do B1, B2, I know B1, B2 don't commute. So which means I need to, suppose I want to do B2 on this. Right? So what do? I can't use this basis. Or I should write this as a linear combination of the other basis. So let me say that I would like to rewrite this is 1, 2, 3, then you will have a 4 and 5, right? You can have 4 and 5, something like this. Okay. So I need to first convert this basis into this basis. This is what we do. So you first have to rewrite this as some linear combination with some coefficient. And these bases, let me call this as U1, sorry, this is anyway R, you don't need to worry. This edge is coming this way. Then let me call it as U1, and then this is U1 only, and then this one will be, let's say, U2, and this is of course R. Yeah? So I need to write a matrix C which makes a change of basis. Okay? So it takes you from, let's say, ST, S1 to R U1 U2 times this, and which one has to be summed up? You have to sum up over all possible U1 U2, right? And what you get, once I have this basis for this, then I can apply the B2 on this. Now the B2 will go inside and act. So you will have the C, ST, S1, R, U1, U2. Let me keep it. Okay. And then the B2 will give you a lambda, lambda U1. Right? Because it is going to, B2 will go and act on the second and the third strand. So you'll have a U1 and Earlier already I have a lambda s. I'm not putting this r comma r, but if you keep track of it, it is always nice. Okay. Many times even here they keep track of the representations which are put on all the. So 1, 2, 3, 4, 5, 6, just to keep track what are the legs carrying represent. Because when you do links, you need to know what are the represent, because that helps you. 1, 2 combined, whatever is the representation will define for you the range of S. Similarly, 3, 4 combined will define the range for T, and so on. Okay. It's nicer to write this in a fashion. So this is the exercise, and what are these elements have to be fixed. Okay. And these elements can be further broken into some fundamental blocks, even at the 4 punctured stage, which I didn't do, right? If I had in the 4 punctured state, if I had taken this basis, I would prefer this basis if I do a braid operation B1 and B2. Okay, so this is an eigenbasis with, let's say, S. I could also have an equivalent basis with a U for the 4 puncture. I did not talk about this because I was just confining to just a closure of a 2-strand braid. But if even in the 2-strand braid, if I look at quasi-plat, even this figure 8, which I drawn here as a closure of a 3-strand braid, I could have drawn a quasi-plat, right? The quasi-plat diagrams are, and then you have a, and then you close it, and here you have something like this. Okay, you can have the same diagram by, this is what I said in the first lecture, that that's a way by master move 1, 2 and 3, you can make it look like a quasi-plat diagram. This belongs to a very nice general class which is called as the double twist knot. Okay. So the way you can draw the double twist knot in most of the pictures, and also you should know that you need to put in these arrows which are oppositely oriented. Okay. So the quasi-plat diagram will never have only parallel orientation. It can have situations where you start following the arrow, then so these are all anti-parallel crossings. Okay. I tried telling you that there is a frame correction, which I fixed that by a closure of 2. If you put m to be 1 or plus or minus 1, I want it to be a knot, and then that way I fix the frame correction for parallel orientation. A similar exercise for equivalence should be done to fix for anti-parallel orientation. Okay. So those eigenvalues are slightly different. So the parallel standard framing eigenvalue, when both the representations are same, that was epsilon s. But if you take anti-parallel, we denote it with the negative sign, and let me call it as T, standard framing. Technically, when you have anti-parallel, as I said, one is ingoing, the other one is outgoing. So you need to keep track that one is a representation, other one is a conjugate of the representation. And the T is an element in R cross R bar. The dimensionality doesn't change, but the T representations will change. Okay, so this will be an epsilon T RR q to the power of CRT by 2. Okay, so we need to fix the eigenvalues accordingly. If it is anti-parallel, because for any quasi-plat diagrams I need anti-parallel. For closure I just need the parallel, and we need to appropriately put things when we do the evaluation of this diagram. Even here it is B1 squared, right? What is the handedness here? You can put a forefinger on the overcrossing and you see that the handedness is negative. And again you can go here and see what is the handedness. You can work. I think this is probably not figure 8. I think there's slight. So the handedness of both are opposite. No, both are positive here or negative here. Right? Did I make a mistake? Yeah, I think this has to be an undercrossing. Sorry, I think. Anyway, you can figure it out. And both of them will be. This is negative, the right? And this one should also be positive. Right? These are positive crossings and these are negative crossings. So you can also write this invariant. Only thing is these two bases have to be related. The same way related here, you can write this as, somebody can explain here, as some CSU depends on 1, 2, 3, 4. Correct? Just like the way I wrote there. For a 4 punctured boundary. Clear? So now you can work out for a figure 8 this diagram very simply now. I'll leave it you to work it out. You may need the state. We did the state for this case. What did we write? We wrote this as summation over S. Right? We wrote this. You can work out for the state which is for this one. Right? I'll leave it you to do this. The way to do it is, you have to add a braid word here. Okay? You add a braid word in such a way that once you add this braid word, this becomes equivalent to this one. Okay? What braid word you will put, will just slide it by a readmaster move 2 and you can make it look like this. Once you have that, you can systematically write the starting state, or equivalently you could put the braid word here and get back the state. Okay? So you know the state from here and you can apply that braid word and then you can get back the state. So for now I will give you that state. Another way of doing this is a glue itself with itself. And what should you get? Again unknot squared. Because if you do this, you will get unknot squared again. Right? So using that also you can write the state for this. Only thing you have to remember is the tensor product of those representations 1, 2, 3, 4. T is between R1 and R2. If one is ingoing and the other one is outgoing, T will be in R1 times R2 bar. Okay. For anti-parallel strands. In the closure you didn't need to worry. But here, because closure, all of them will be parallel. So you did not have this problem. But here you have to see, if this is anti-parallel, then your representation which you put S will involve R cross R bar. Okay? Is that clear? So that's very important. Now let's glue this and get what is the answer for figure 8. Okay? So So figure 8 answer will involve summation over S, dimension QRS with a square root with this. Is right or the other way around, right? So I can go from here. This one is that state, right? Fine. On this basis, I've just written the state. Technically, I should have written this as a dual state. That's all I need. Okay? Square root of. These are all square root of. So if I put this in, then I do the operation of the right word. So this state is not okay. This is the right state because this is the bottommost piece I'm writing. Okay. And then I'm going to do the braiding operation V1 to the V1 twice. That is it with negative right. Right? So you will have a V1 operation which is done twice. I put an inverse squared, and I have to also remember that it is anti-parallel strands. Right? So let's write the eigen. It's an eigenstate. Is this clear? So what will the eigenvalue be? Lambda t r comma r bar the whole squared, and in the anti-parallel case the r comma r bar also takes care, you don't need to put a minus sign, the square. Okay. After that I have to again change the basis because I have to do B2 square. Clear? So basis change has to be done on this. How will that be done? You will introduce an S, then you have a CTS 1, 2, 3, 4. I'm not writing what those are, but we can write it explicitly as R bar, R bar. You can put that later. And then you have a basis which is right. And now we will hit the B2 squared, and B2 is, this is with the right 2, so I have to put the negative 2, and this is with right plus 2, so you will have a lambda s. This is for anti-parallel strands square, and then we have to cap it. The capping defined by, you can call it as S prime, and then you will have a delta S prime. So capping will give you so you have to take an inner product. Fine. When you take an inner product, they are basis states, so delta S prime. So ultimately, what do we get for figure 8? Normalized version for figure 8 with any representation R will be summation over S and T, square root of dimension Q, RT, square root of dimension Q, RS, CTS, 1, 2, 3, 4. Those are the external punctures which carry the representation. You also have a lambda RS, anti-parallel eigenvalue with -2 and +2, right? So one is RT with +2 and lambda RS. That is -2 and this is +2. That's it. That's the invariant for the figure 8. Dimension Q of R and all I have told you is the function of Q. I have not told you what is CTS 1, 2, 3, 4. This diagram which I have drawn here, you could manipulate both with the same right you can draw. Okay, so those are, and you can put even number of crossings here, even number of crossings here. If you do that, they will, so you can call that as a twist knot with 2m, 2p. A double twist knot with 2m crossings here and 2p crossings here. Here 2m can be positive and 2p can be positive, or 1 can be negative. If 1 is negative, then with m and p being 1 and 1, you get the figure 8. In the most general class, I can write the invariant and I can write the polynomial form if I know this coefficient. You know the change of basis, correct? And that change of basis should also be a function of Q. Then only I will write the expression and check whether I get the figure 8 Jones polynomial if I put fun in it. So this CTS 1, 2, 3, 4 is what we call it as a CTS 1, 2, 3, 4. Remember that T is an element of R1 cross R2. It is also an element of, if you had looked at the diagram, if you see the diagram, the T, right? Is that the notation I am using? It shouldn't, CTS is what I am using, right? Yeah. From here you can see that T is 1 cross 2, or it can also be 3 cross 4. But 3 cross 4 should be in the opposite direction. Okay, so 3 cross 4 should give you a T bar in some sense. You see it from here, it is T. Should be. So you can write this to be R3 bar cross R4 bar. Similarly, S will be an element of, you can see from this, the S is an element of 2 and 3. Okay, so S should be an element of R2 cross R3, or it can also be written as R1 bar cross R4. Okay. Sometimes you have to take a common intersection of both. Okay, if all the 4 representations are different, then the common intersection will define for you the range of S. Similarly here, now you have to take a, I have to put it as intersection of R1 bar cross R4 bar. Here also I will write it as okay. So this is very important. So this coefficient in the twist knot, if both the rights are same, if I interchange the 2m and 2p, okay, you will not get a new link. Using that property, you can show that this has to be symmetric. Okay, I'll leave it you to check, because you will change T and S, because if you exchange these two pieces, you will show that this T and S interchanges, does it affect these two? The only way the result will be the same, because invariant is the same, will force that T and S has to be the matrix which I am going to write, the two index power matrix should be symmetric. That's one property. And there are many more properties from topological equivalence of knots which we can use. Many of the properties fixes some identities for this CTS. The identities are exactly similar if you see the quantum algebra people, or even in the conformal field theory, they do see that it's exactly similar to the duality matrices. All these properties, pentagon identity, hexagon identity, can all be shown by equivalence of the diagrams. Okay. So essentially, this is proportional to, so let me write that CTS 1, 2, 3, 4 is proportional to what we call it as the Wigner 6J symbol, which is R1, R2, T, R3, R4, S. Just like your Wigner 3J involves Klebsch-Gordon coefficients, these are sometimes called as the Raka coefficient, and the properties of this transformation matrix, which relate one basis to the other basis, which you have to do to get the transformation to do the polynomial invariant, and that transformation we know it is 6J symbol, and these values are known for SU2 explicitly. There is a closed form algebraic expression by Kirillov-Reshtikin which tells you those coefficients. They are functions of Q. Plug in those functions of Q here for fundamental. 1, 2, 3, 4 carry fundamental. Leave it you to do that. Like that matrix I can write for you if you want. The matrix is okay, I think it is 1 square root of 3. It's symmetric, right? It's -1 or something. That is what from the Kirillov-Reshtikin formula for fundamental. If all 1, 2, 3, 4 are fundamental, then T will be either this, S will be either this, so that matrix is this. So substitute that and you will get the polynomial for normalized polynomial for Jones for the figure 8. Okay. So I think I have given you some flavor. This procedure is not stuck to only 4 punctures, but 6 punctures becomes even more tedious. You can see that you need these kinds of bases, change of bases and so on. Whereas if it is 4 punctured, I have to only play around between the spaces and the spaces. It's a lot more simpler. So many times any diagram, like for example the pretzel diagram, we can draw it as, the simple pretzel which you might have all seen. You could have a anti-parallel with 3 crossings here. You can have another anti-parallel with 3 crossings here, right? And then you can close it. Okay, if you want to do this explicitly, you see that you have to work with 6 punctures. Interestingly, the same diagram can be drawn I could draw it as some kind of an object, okay, with the 3 anti-parallel crossings here, okay. I can do this, which is 4 punctures, okay, and I will have an intermediate stage, which is This is again a 3 ball with 3 S2 boundaries. I insert it here and then things all become much easier. You can put the 3 crossings here, anti-parallel, close it, and similarly here you can put the 3 crossings here and close it. Okay, these two are equal. So what is the advantage? I've been able to draw this pretzel knot. You can draw this diagram explicitly. It's a knot actually. You can again see that it involves gluing 3 balls where these is with single boundary, triple boundary, single boundaries. Each of these states I have explained to you how to do it. Right? I have not explained to you how to do this, but there are some equivalents which you can see, right? If you have this and if I glue this with this, we can make it equivalent to looking at 2 boundaries, right? You can push it, pull it. Can you see that? You can actually pull this, stretch it, make sure that this is not there and you can make it like this. Using equivalents of 2 boundaries, again you can cap this, then you will end up getting this to be equivalent to only this, right? All these things you can do. Consistency, and we can fix all these states which are multi-boundary states, and we play around only with 4 punctured boundaries and get many knot invariants using these Raka coefficients. Computation becomes simpler, and the knots which you can draw this way are called arborescent knots. Not all knots I can draw. So arborescent knots are ones which I can draw with 4 punctured boundaries, but the boundary can be more than one. There is a knot which is 818 in the Rolfson table, which I cannot, whatever I do, I cannot redraw it this way. I need 6 punctured boundary there. Nothing I can do. Then I go through this other procedure which I was saying, and it is little tedious, but it can be worked out for SU2. For SUN, you need those Raka matrices. Even these Raka matrices for low dimensional representation I know for SUN. But if all the representations are same or conjugate, I know from an indirect method. But it's still not available. I don't know what is the Raka coefficient. When these are so this for SUN is still a question mark for arbitrary R1, R2, R3, R4. Okay. So we cannot find the polynomials for SUN because this is not available. Okay. So this is where I hope you got the flavor of how the systematic exercise can be done simply by playing around with the conformal blocks. These bases which I have drawn is sometimes called as a conformal block basis, and we can go from one basis to the other, equivalent basis, and that basis is given by this quantum Raka coefficient or quantum vector 60 symbols. SU2 is completely known. Any arbitrary knot, we can work out the polynomial. I have not had the time to tell you about the 3-manifold invariants. The only requirement is that you should be able to sum up over all the representation placed on the knots. So they will be the normalized invariants, and you have to put a coefficient which we'll call it as mu r, and make sure that if you go from knot K to another link by a Kirby move 1 or a Kirby move 2, you will have summation over R and R1, mu R1, and then you will have a link with different representations And here we are going to work only with vertical framing. So it's not V, it has to be regular isotopy invariant. And this will be the link invariant of regular isotopy where we know the eigenvalues with different representations. For a link where this link is related to this not by either Kirby move 1 or Kirby move 2, you have to impose this. And then if these two are equal, then you call it to be a good candidate for a three-manifold invariant. And you have to figure out what is this mu r. And this mu r can also be fixed. Okay, so let me not get into it. Anybody is interested can look at my papers 1991 and 2000. One with Ramesh Kaul, the other one with the mathematician. What we did is, if you give a 2 cable of a trefoil, what they replace is every strand is replaced by a double strand, and you have to draw the trefoil. Okay, so you can put the braid word with strands being replaced by a double strand. You understand what I'm saying? So they have given, Licorice has given a nice formula for a three-manifold invariant involving such 2 cable, 3 cable, 4 cable and so on. So large number of cables summed up. Whereas we had a formula where it was summed up over all representations. And what we could show is that the 2 cable should be seen as tensor product of fundamental representations. And if we see it, this expression, we proved that this expression is exactly same as the Licorice three-manifold invariant, which was written in terms of bracket polynomial, but we could relate the q to a by q to the power of 1/4 to be the bracket polynomial, I think minus with the bracket polynomial variable, and we showed it's one and the same. So this was a paper with Swati Nayak. Okay, so this is probably 1999 on the archive, and 2000 it is published, where we showed the equivalence of cabling corresponds to tensor product. And this work was with Kaul, where we had it in probably 2000. Okay, so let me stop here. If you have any questions, I can answer, otherwise I will stop here.
So let's answer some questions.
What's the Hilbert space interpretation of this sort of pair of bands there?
Which
So
one? This one?
No, in the arboration of the
Hilbert space. So
Yeah.
you can have a 3-ball, Chern-Simons functional integral on a 3-ball, but it has 3 boundaries.
Okay, but so this the cap correspond to a state.
You can put a, yeah, so that's a good thing. So what you can write is, like, if I want to write a 2-boundary state, it is to be a tensor product of boundary 1 and a boundary 2. It belongs to the Hilbert space of S2 for 1 S2 boundary times Hilbert space for S2 with the second S2 boundary. So if I write a state here, for example, if I want to write what is this state, right? For the 2 boundaries with 4 punctures, I should write that state as something which is involving for the boundary 1 multiplied with state which is involved for the boundary. That's the way you have to do. Because when you glue things, when I glue things the way I am doing it here, suppose I call this as boundary 1. I will call it oppositely oriented boundary as 1 prime, 2 prime, 2, 3 prime, 3. So the gluing inner product should be between the states in the common boundary. You can't do the inner product with boundary 1 when the common boundary is 2 and 2 prime.
Okay.
So you have to take care of that. Okay. So this is the state for the 2 boundary. For the 3 boundary, it will involve, if you had 3 boundaries, then that state will turn out to be RS, 1 over root of dimension QRS. And you have boundary 1, boundary 2 and a boundary 3. Each one is the same. Okay. Okay, So there's something which I did not really spend time in telling you is that sometimes the multiplicity, I did say that sometimes this RS can come with multiplicity, and there are some careful things had to be done here if you even want to go to SUN representations of this type, and that has been done by Ju and Jokers. I think it's Ju and Jokers. Okay, this came out probably in 2015 or 14, I don't remember. Okay, but that has to be done, 14, right? So that has to be systematically done. Right now I'm assuming everything is symmetric representation, no multiplicity, so we don't need to worry. But if you have multiplicity, then you have to be a little more careful. But the multiplicity, the bonus is that there is a class of knots which Jones, Kaufman, Homefly did not detect, but we could detect it because of that multiplicity. So multiplicity plays an important role. So if mathematicians give me an example that they are not able to detect this, from Chern-Simons I can change the gauge group, I can change the representation. I could try and see whether that can be detected, but that's not proof for classification. It definitely has improved the power of classification. Then the computation is also very elegant. We can actually systematically do it. Right. Let's stop here. Yeah.
Okay. So let's thank the speaker again for the entire series of
Thank
lectures.
you.